Hello everybody, and welcome back to the channel. Today we're going to be doing another low-level design video, back by semi-popular demand, not very popular though. And today we'll be designing an elevator. Without further ado, let's get into this low-level design. I've thought this out at a medium level, and frankly, I could have done a much better job here. So anyway, let's do this. Okay, so in today's question, we're going to be designing an elevator system. And the kind of tough part about this problem is there's really not that great of a solution. It's one of those things where there are many different types of implementations that we can do, and they all have their benefits and their trade-offs, and we're going to try and discuss those a little bit. I'm not going to do a super deep dive. There are videos out there that cover this problem for 45 minutes, but truthfully, I think parts of those videos are kind of overkill, and I'm going to try and just get to the root of the problem relatively quickly to help you guys out. Okay, so let's think about the elevator itself, because we know there's got to be some sort of elevator object, and the reason that I'm choosing to use an interface here, at least to get started with, is there may perhaps be multiple different implementations of an elevator, right? We know there's going to be this box that lets people in it and it's going to ride around, but the way that the elevator chooses where to go next is potentially going to differ. We just know that it's going to be moving around through the elevator shaft. So with this in mind, I just have one method that I want us to implement called move. And basically all that's going to happen then is the elevator basically says, okay, what floor am I going to next? And go ahead and do that. So basically, in addition to that, we also need some sort of dispatcher interface. The reason for this is, yeah, sure, the elevator can basically have some sort of state telling it where it's going to move in the future, but sometimes rides are going to have to be requested by humans as they, push a button or two, and the dispatcher is going to be responsible, generally speaking, for basically sending new requests to specific elevators. Now, depending on our implementation of the elevator system, this may be either done passively or actively. So a passive dispatcher would basically be waiting for an elevator to request, a new passenger. Basically, the elevator says, I'm empty, can you tell me where to go next? An active dispatcher would basically say every single time that someone who requests a ride presses a button, it already is going to assign an elevator to that request the second that it's made. So that would be the difference between kind of an active and passive dispatcher. And the issue with that is, it makes defining an interface tough for this because essentially those are two completely different interfaces between the user and the elevator system, right? In the passive case, I might just press, the up button or the down button, and, an elevator is going to swoop by me at some point and pick me up. And in the other case, I would probably press my destination floor, and then I would go ahead and see the elevator that I have to go to and go to that elevator. So it's kind of actually two different interfaces. So at least for now, the interfaces that I'm defining are assuming kind of something like a passive dispatcher, where the elevator is going to wait until it needs to have more riders, and it's going to ask the dispatcher where to go next. So what are some methods that we can actually go ahead and define? Well, there's the add elevator request method, which is going to take in a current floor and this parameter moving to. So I left this purposefully vague because, again, depending on the type of buttons that you're using, moving to could either be a destination floor or it could be something like up or down. And add elevator request is basically, what the user or the button would be telling the dispatcher when they're trying to go ahead and request a ride from the elevator. Similarly, we also have this concept of removing an elevator request. This is because sometimes requests get handled. It's going to be the case that sometimes an elevator may swoop past someone who has an active request and just happens to pick them up. And as a result, it's important that we can then remove their request so that no other elevators in the future are going to go ahead and try and grab them later. And then we also have this concept of getting a request to handle. This is where, in like the passive case, I, as an elevator, am going to ask the dispatcher for the next request to be handled. And it is the dispatcher's job to basically do some sort of logic or have some sort of state that it is going to tell me where I should go next to pick up my next passenger. And then also we have this concept of has unfulfilled request. And this is going to come in handy basically if I'm an elevator and I'm passing by a floor and I want to check if there's an active request there where I can pick this person up potentially and go ahead and, kind of add them to my existing elevator ride in order to kind of parallelize the number of passengers that we have. But let's move onwards a little bit. So another aspect of kind of object-oriented programming that I personally have debated here is whether we need a button class. I think that you certainly can use buttons, and this is obviously something that you want to work out with your interviewer, but the only reason that you would want to make an explicit button class is if the buttons themselves need to have state. So in reality, when you press a button when you're waiting for an elevator, typically it'll do things like light up, and when that request is handled or when the elevator comes to get you, the button will stop being lit up. So in an example where we care about the state of those buttons, then obviously we do want objects representing each of them. However, in our basic elevator system, I'm going to imagine that even though there are buttons, what the passenger is really doing is just calling a dispatcher method to add a request. And so as a result, I've chosen to not involve buttons in this to try and simplify the problem for us. But if it did come down to it, we could obviously have a bunch of these buttons where, there would obviously need to be some sort of method to communicate with the dispatcher service to add a request, and also there would need to be some way for the dispatcher service to communicate back with each button once a request has been handled or, is starting to be handled, and then the button could maybe turn off its light or something like that. So again, I'm purposely leaving these out of this problem in order to, stop it from getting too overly complicated. I'm just leaving this to elevators and a dispatcher service for now, but in a real world, obviously there's going to need to be some sort of button classes. Okay, so one comment that I received on my last video was to kind of, exemplify how dependencies were passed together and, look at the actual driver code just to go ahead and wrap things together. Basically, we know we're just going to have one dispatcher service because that's going to be a centralized thing where all the requests are handled. And then I'm imagining that the dispatcher service is going to be passed into each instance of an elevator that's created. I've created 2 here, but you could obviously create, 3 more, 100 million, whatever. We're assuming that our elevator system is, potentially limitless, because if it were a finite size, then the complexity of our operations wouldn't really matter very much. Additionally, I'm not going to talk about it very much in this problem, but again, if we assume we have like 1 million floors or something and 10,000 elevators, we could in theory almost shard up the floors such that each elevator is handling different parts of those floors. But I think for the sake of this problem, that's probably not too important, and it's kind of an afterthought for this. I think if your interviewer was asking you about that, it starts becoming a very different problem, and this is more just about the design in general. So all we're going to do in the main method is just run a while loop where we're calling move for each of the elevators. It's possible that these methods would be running concurrently in reality, and if that's the case, we're going to need some amount of locks in order to make sure that the same request isn't being sent out to multiple elevators. But for now, I'm assuming that we're just running this in a single-threaded system, and again, that should hopefully simplify things a little bit so that we don't have to think about locking. Okay, so what is a naive elevator implementation, right? Because I mentioned that all the elevator really needs to have is this one method called move. That's really all effectively that an elevator is doing, is it moves from place to place. It changes direction potentially, and it opens and closes its doors. I didn't even really cover the opening and closing of doors in this problem, but I'm just assuming that whenever the elevator is idle, it's going to open its doors, or whenever it, whenever it switches floors basically, and picks up a passenger or drops off a passenger, I'm just assuming it's opening up its doors. But basically we have this concept of a naive elevator implementation. So the easiest way for an elevator to work is we just handle one request at a time, right? We basically take them in as if they were a queue. The elevator would hold one request locally where it would go to a floor, it would open its doors, it would go to a floor, it would open its doors, and every single time that it drops off a passenger, it would then again just, receive a floor to go to and go ahead and do that. It's not overly challenging, and the reason this obviously isn't going to be very good is because we're traveling a lot of redundant distances. And what do I mean by that? Well, let's imagine that basically I'm in the elevator, that's me in the gray box right there, and I'm going upwards. And then, we see that there's this passenger Elon who could also be picked up in a manner such that, we're now traveling duplicate distances between, where he wants to be picked up and my destination. So we would minimize the distance traveled by the elevator in the event where I'm picking up Elon and I'm also dropping him off at his own destination, if we do that during the course of my route. So doing this, we can basically handle a few requests in parallel, and we don't just have to handle one request at a time and then go ahead and handle another. That wouldn't be very efficient. So let's look at some code that might actually be able to implement some logic like this. Okay, So as you can see, here we have our kind of elevator algorithm implementation. We know we have some local dispatcher, and for now I've called this a FIFO dispatcher, which at least for me means that it is going to basically give you all of the requests that haven't been handled in the order that they were submitted. So again, it's just going to be a queue dispatcher, but we can talk about different types of dispatchers later in the video, and I'm planning on doing so. Additionally, we're going to have this basically local element called floors to visit. And floors to visit is just a list of all the places that the elevator has to go. I'm implementing that as basically a doubly linked list with a hash map. The reasoning for this being that not only do we want to be able to remove kind of from anywhere in that doubly linked list in constant time, but we also want to be able to quickly see if things are in there. And we'll speak about that a bit more. And then we also have this concept of current floor and current direction, because this is going to help us determine whether we should pick up a rider and the direction that we're currently moving in. So basically we're going to do the following. If there are no floors that we need to visit, all we're going to do is ask our dispatcher for, basically the next request up. Recall that our dispatcher is a FIFO queue, which means that we're just going to be getting the first request that was sent in chronologically. And then we would go ahead and add that to floors to visit and basically go ahead and set our direction, because the direction is going to be corresponding to whether the passenger pressed up or down. So we're going to be getting that from basically our dispatching service. And then from there, again, the next floor that we want to be visiting, where we're assuming floors to visit is a queue, we're just going to go ahead and pop from the queue, and then use a while loop to go ahead and loop from our current floor towards the next floor based on kind of the current direction. And then finally, we're going to say every single time that we go ahead and go up and down a floor towards our destination floor, we're basically going to check if there is a request from that floor in the direction where we're currently going, right? So if we're going down and we pass a floor and there's someone who wants to be going down from that floor that we pass, we're going to go ahead and pick them up and push their destination floor to the queue. Right here, I'm kind of making an oversimplification in the sense that I'm assuming that the passenger is kind of coming in and definitely pressing a floor that's in the direction that they indicated by the elevator buttons. In reality, that's something they don't necessarily have to do. But the point is, the passenger is now going to, also give some sort of floor that they press within the elevator, and we're going to put that at the back of our queue. We want to visit it eventually. And then another aspect of this is, as we're actually moving in the elevator, if the current floor that we're on is going to be a floor that is in our floors to visit hash queue, it means that somebody in our elevator wants to get out at that floor, and we should stop and remove that floor from floors to visit and let that person get out. Again, I'm kind of taking out of the problem the aspect of actually stopping, opening the doors, etc., etc. That's not too hard, you can add that all back in, but by saying floors to visit dot remove current floor, I'm insinuating that the passenger is getting out right there. So basically we keep doing this until we run out of floors to visit, at which point we ask the dispatcher queue for another place to go. This is kind of known as the scan elevator algorithm, the reasoning being that you basically just keep moving in the same direction until you're out of places to go, and then you can ask for a new place to go. Some variations of this are, as opposed to like ever stopping and potentially changing directions when you're out of places, you could just go all the way from the bottom of the building all the way to the top and back down and back up and back down again, but that potentially means that you're going to be wasting some travel time. Okay, so what are some issues with the previous implementation of the elevator class that I just described? Well, there are a couple. The first is that for code simplicity, I decided to basically run a while loop of all the floors from our current floor to our destination floor, so that at every intermediate floor we could check if there are passengers to pick up or if there are passengers to let out. However, this could technically be improved algorithmically. The reasoning being that, let's say our building has 1 million floors and I want to go from floor 900,000 to floor 500,000. That means I'm running through 400,000 iterations of a while loop. But what if there were only 2 potential, passengers that entire time? Well, that's kind of a big issue. So it would probably be better if we could just go ahead and iterate through the actual requests that are still outgoing and the current passengers in order to figure out where to actually stop at and use the logic there. Something like a binary search tree here would be hugely helpful in the sense that From one node in a binary search tree, we can easily figure out all of the nodes that are greater than it and also less than some other node in the binary search tree. So to put that, in kind of a more concrete example, if I'm going from the 20th floor to the 40th floor and I have all the dispatcher requests in one single binary search tree, it means that I can go ahead and figure out all of the requests in the dispatcher that are between 20 and 40 in linear time complexity, which is really, really good. In fact, even better than linear time complexity, because you just go to 20 and 40 in the binary search tree, and then you basically get all the nodes between them. Another issue that I didn't really talk about too much, because I've just kind of assumed so far that the dispatch scheduler is a FIFO queue, is that we could have starvation. So what if the dispatcher wasn't something where it was just first request is the next one handled, and instead it was, if you're an elevator and you don't have any passengers to handle, go ahead and handle the request that's closest to you. Now let's imagine there's one guy who's been waiting at the lobby of a building, and all the other requests are popping in at the 100th floor. The guy at the lobby could have been waiting for an hour because the elevator just keeps servicing all those requests, from the 90th to the 100th floor and bouncing back up there, and then the lobby request gets starved. So it's important to kind of think about how we actually build out our dispatcher in order to make sure that we're not going to be starving specific requests. So with this in mind, what would actually be a starvation-free dispatch service that is also algorithmically sound? Well, I kind of described it before with that idea of a FIFO dispatch service, but the general point is we can again use a doubly linked list and a hash map. The reasoning for this being that we can, easily pull the first thing out of that doubly linked list. That's going to be the oldest request, so it works as a queue. But also, if we just happen to randomly service a job because we were very close to it, or because, we passed the floor that request was coming from and just happened to pick that guy up, we can then remove from an arbitrary place in that doubly linked list and hash map combination in O of one time, which is really great. One issue with this, however, is that just doing a FIFO dispatcher doesn't account for the actual distance that an elevator has to travel in order to handle that next request. So let's imagine that we have a really tall building and we have two elevators, and one elevator is all the way at the bottom and one elevator is all the way at the top. And the top elevator asks the dispatch service for the next request to get. And the next request to get happens to be from the lobby. And the bottom request service asks for the one after that. And that happens to be all the way at the top of the building. Now we have two elevators going in the complete opposite directions of one another all the way across the building and wasting a ton of distance traveled. It would be better if we could somehow take into account not only the time that a request has been waiting, but also the distance that the elevator has to travel to service it, so that we both don't have starvation, but also minimize distance traveled by an elevator. This would be something like a starvation-free and distance-conscious dispatch service. That is a lot to say. But the general point is we would just create some sort of metric that takes into account both distance to the actual request from the elevator's current location and also the time since each request. And this is really great. It should, minimize the amount of distance traveled while also not starving jobs. However, it comes at the cost of being algorithmically inefficient in the sense that we now have to calculate our heuristic for every single one of the open requests, because it's not like we can use a priority queue here, since the amount of time is always changing since a request has been made, and so is the distance to any given elevator. So basically we'd have to iterate over all open requests whenever an elevator is like, can I find a new person to pick up? And that could take a lot of time if there are a lot of requests, but this is another alternative option that you could in theory discuss in your interview. And then finally, the last thing that I want to quickly touch upon, which I touched upon a little bit earlier in the video, is the fact that some of these elevator systems are built a little bit differently, where you don't just press up or down when you get in, but rather when you're actually requesting an elevator, you punch in your destination floor. There would be like a keypad or something, and then the dispatcher system would actually assign you an elevator from the beginning. So if this was to be the case where we decided to go with this type of service, well, there are a couple of interesting things to think about. And I'm not going to get into this too much because I think it's honestly a little bit beyond the scope of this interview or this interview question. But the first question would obviously be what type of interface are you looking at? And it would be quite a bit different, right? Like the dispatcher service, every single time you pressed a button, would have to actively assign you an elevator, and then your floor would go into that elevator's queue of floors to visit. But more importantly, Another good question would be, what type of heuristic would we actually use as the dispatcher service to determine what elevator is going to service which request? We don't care about the time since a request has been made anymore, simply because of the fact that the elevator is going to be assigned instantly right after the request has been made. So time since the request now becomes inevitable. We'd probably be thinking more about things like, the capacity of each elevator. We would be thinking about things like the distance from the elevator to the person. And again, the dispatcher service, this would potentially be a linear time operation over the number of elevators. So if you have millions and millions of elevators, the dispatcher service has to loop through all of them, calculate some result of a heuristic, and then assign that request to one of those elevators. So that is something to keep in mind. In conclusion, though, this is obviously a hard and very open-ended problem. There are multiple different implementations of elevators, and that's because there's not one that's objectively correct. This isn't like tic-tac-toe, where there's just a pretty easy, straightforward answer once you have the class system down in terms of algorithms. It's actually the case that, depending on which elevator style you choose, we might have a completely different interface. And so in conclusion, the slide says it, but elevators blow, and so do I, but a lot of guys. Alright guys, well that's all for today's video. Fortunately, it is getting cold enough here in New York such that I stopped sweating every single time I record, which is a real good thing for me. But yeah, I'll see you in the next one. Again, let me know how I can improve this series further. I understand this is very open-ended, and it's hard for me to even necessarily come up with the answers sometimes that are satisfactory to everyone, but I will continue to do what I can.